Welcome everyone. In this video we shall address the area of polar curves, and I'll work out 3 examples for you, so I hope that you will find it helpful. So imagine I have a curve in polar coordinates, r equals a function of theta, going from some theta 1 in blue to some theta 2, okay? And we want to find the area enclosed by these 2 line segments in black and this curve in black. And so what are we going to do? We're going to use the same technique we have used with rectangles when we were working with the rectangular coordinate system, the Cartesian coordinate system. So what do we want? Well, what are we hoping is to create a bunch of little slices of circles. We call them sectors. So I'm going to just partition this into 5 pieces just so you see the point. Now, if I were to consider the shape under consideration, and if this is a sector like this, going like this, it's easy to find the area of a sector using basic geometry. The problem is the area of a sector will be a lot larger than the area under consideration. But if I partition this into 5 little segments and I create small sectors, I'm still not going to get the right answer. But this new technique helps me approximate the area better. So what I'm going to do quickly is I'm going to borrow one of these sectors here, put it here. And initially what I have is this curve here, this little shape with the black and the 2 blind line segments, which we can't figure out. But if I were to extend this and create a slice of a sector, it's we know that we are actually overestimating, right? There is a little area here that we shouldn't account for. But if I do this over and over and over again, infinite many times, this little areas start to shrink. It actually becomes 0 when the subdivisions are infinite. Okay, so that's the whole idea. You may remember from geometry that the area of a sector is half r squared theta. And that idea came from a simple concept. We know the area of a circle is pi r squared. And if you are interested in the area of a sector, you could just hit the area of the circle by take a portion. This is called a portion of the circle. You know, if this is, let's say, pi, then you have pi over 2 pi, which is a half, and it makes sense. The area of half a circle is pi r squared times a half. So a portion of the area of a circle gives you the area of a sector. So it's not hard to find the area of a sector, not the one in question. And notice that the pi cancels, and you end up with half r squared theta, or change in theta, okay? Which is exactly what you are accustomed to. So if I were to add all of these finitely many sectors from 1 to n, I would have half r squared. This is just r squared. Now notice I didn't write f squared of theta. I wrote f squared of theta I, because you are hopping from theta 1 to theta 2 to theta 3. So look here in red. So if I were to consider this little first sector, and I go halfway through with the red dots, so that would be theta 1. If I move to the next sector, my second angle, theta 2, when I is 2, you get theta 2. It goes from the x-axis to the middle of this sector, and so on and so forth. And then theta 3 will go to here, and theta 4 will go to here, and so on and so forth. But essentially, this is just r squared and delta theta. So I'm literally just copying this, but by adding these sectors one after another. Now, this is not the area that we are interested in. That's why I use an approximation sign. So this approximates the area of the region that I'm interested in. But to make it the area, to find the area of the region we're interested in, you better change you better push n to infinity. In other words, if we take a limit as n goes to infinity of this, which means if I partition this region infinitely many times, then basically all these little tiny areas that I'm skipping here, they're all going to shrink to 0, okay? And by definition, so this is going to be basically the Riemann sum. So this is the discrete case, right? But once you add the limit, it becomes the continuous case. So I put an equal sign now. This is exactly the area I'm interested in. And of course, the discrete case becomes the continuous case, going from some theta 1, let's say this one in blue, to some theta 2, the last one in blue as well, okay? Half r squared d theta. Notice that when n is large, delta theta becomes d theta. D theta is just a tiny infinitesimal piece of this, okay? So this is basically the formula that allows us to compute the area of an area in polar coordinates. Now here's the good news. The arc length had a square root in it and had a dr d theta and r in it. In here we just have r squared. We don't have dr d theta. And obviously we don't have a square root, which is a huge relief, because that square root creates a lot of problems in trying to find the arc length. So now you're going to have less of a problem evaluating the integral. So let's go through 3 examples quickly. So I just wrote down a simple relation in polar coordinates. R of theta equals 4 sine theta. And as you know, the sign always goes up and down. 4 is the edge, and therefore the center is 0, 2, and the radius is 2. And we want to find this area. Well, you know what this area is. This area is pi r squared, and r is 2. So we should get 4 pi's, okay? Now, let's do it the way using the formula that we just came up with. Now notice this. Here is your half r squared d theta. Now, why is it that we have to go from 0 to pi? If you go from 0 to 2 pi, by the way, you're going to get 8 pi's, which is twice the area under consideration. So that's one thing to keep in mind. Just because you see a circle, it doesn't mean you go from 0 to 2 pi, because this is not centered at 0, 0. In fact, when r is 0 at the pole, let's say we're going to march in this direction, you are facing an angle of 0, right? And at this point, you're facing this angle here. And you keep moving, and then you come back to the pole. Now you're facing pi. So your limits of integration are 0 to pi. So please don't write 0 to 2 pi. Again, 0 to 2 pi will give you 8 pi's, which is silly, because we know that the area, before we even start, is 4 pi square units, okay? And this is a very easy concept. I can walk you through this quickly. 4 squared is 16 times half gives me 8. Still going from 0 to pi sine squared. We're going to use the double angle formula. I'm going to try to isolate sine squared, right? So sine squared is 1 minus cosine 2x over 2. I dump it in here. I pull the 2 out, so that 8 becomes a 4. I should say I pull the half out, okay? So that gives me a 4. And you're left with this, and you all know how to integrate this. This is just theta, and this is just negative a half sine 2 theta. Make sure that you use the chain rule the other way, the reverse way, so it works. You go from 0 to pi, and that should give me 4 pi's. Once again, this is the second time we're using this double angle formula. It comes in very handy. So if you have a power function here, a power trig, you better reduce the power. Okay, don't think of this as a power rule, you know, like sine cubed 1/3 sine cubed or something of that sort. You don't have the derivative of sine sitting in the front. If you have a cosine, that's a different discussion. In other words, if you have a cosine here, sine squared, that would be a different discussion. All right, so let's do another example. I recall that if on the cosine, okay, if you have an even constant here, you just get a double paddle. So if 2 gives me a 4, if it's 3, you'll end up with 6. if it is an odd number, you'll get the exact number. So if you have cosine 3 theta, you're going to get 3 leaves, okay? 3. Now, this one just tells you how far you can extend. So goes all the way to 3, goes all the way to 3, all the way to -3, and all the way to -3, okay? So that's what that means. And I wrote 3 just so I can make my curve look a little better. If I had cosine 2 theta, it'll probably end here, and it'll be very hard for us to see. And I'm not going to go through the entire process of integration, but I want to address the limits of integration. So we have r squared d theta and a half. I took the half out, okay? So I took the half out. So r squared d theta. Now, what are the limits of integration? Well, some of you could probably guess them. So if you draw a tangent line here and a tangent line here, you could see that this is pi over 4. And this one is 3 pi over 4. But you don't want to go from 3 pi over 4 to pi over 4. You want to go from a negative pi over 4 to pi over 4. You want to go from a smaller angle to a bigger angle. So some of you could guess that very quickly. What if you couldn't? Or what if this is tilted and it's very hard for you to see? What you want to do is force r to be 0. In other words, at the pole, let's figure out what are those angles that give you these tangent lines, right? What are those angles? When r is 0, you get 3 cosine 2 theta equals 0. I knocked off 3. That means 2 theta, cosine 2 theta equals 0. That means you are at, you are here or here, right? And so that means the 2 theta has to be pi over 2 plus multiples of pi's. If you add pi, you get to here. If you add another pi, you get to here. If you subtract pi, you go to here. So k is an integer. Okay? And what you do, you solve for theta. Now notice what I did. I didn't divide by 2 until I add this piece. So make sure you add the k pi before you divide by 2 across the board. I get pi over 4 plus k pi over 2, where k is an integer. So when k is 0, you get pi over 4, expected. When k is 1, you get 3 pi over 4. If you keep going, if k equals 2, you get 5 pi over 4, which is exactly pi over 4. Is it? Pi plus pi over 4 is 5 pi over 4, yeah. All right? So it takes you back to the same position. Second thing to notice is I expected only 2 angles because I have a double angle. So if this is 3 theta, you expect 3 angles, okay? Just so you know. Now, you could set up k to be -1. You get pi over 4 minus pi over 2, which is negative pi over 4. So that is essentially this. But when you put limits of integration, you don't want to use this one. You want to use that one, okay? So these are my 2 angles that we thought of earlier. Now, the next thing you do after you find your angles, your potential angles, you want to make sure, this is important, you want to make sure that dr d theta is not 0 at these angles. So look in here. Dr d theta is -6 sine 2 theta. And if you plug in pi over 4, you get sine of pi over 2, which is 1, and 1 times -6 is -6, which is not 0. That's good news. And if I plug in negative pi over 4 here, I get sine of negative pi over 2, which is -1. -1 times -6 is 6, which is not 0 again. So that's okay. So once you get your angles, let's call them potential angles, you want to test them under this fact. You don't want dr d theta to be 0 when you plug them in. Okay, so they do qualify, so you put them in. Notice something else I did. If I'm looking at one leaf, only this leaf from negative pi over 4 to pi over 4, it is a good idea to go from 0 to pi over 4 for 2 reasons. Reason number 1, if you exploit symmetry and you go from 0 to pi over 4, obviously you have to double your integral, so that half disappeared, and I took the 9 out, okay? So these are the same. The reason you do that is because when you evaluate at the end, it's easy to plug in 0. That's one reason. Here's another reason. Sometimes if you don't do that, and you evaluate this, you actually might get 0, which is silly. We know that this area is not 0. Okay, in other words, you might get stuck with the idea of square root of cosine squared is plus or minus cosine, so to speak. So be careful. I would exploit symmetry anytime I can. And just like I did here, you use this trick again here and finish the problem on your own. Okay, I'm not going to finish it. But I did this problem for many reasons. To show you the shape, talk about this 3, what does that mean? To talk about the limits of integration, to talk about exploiting the idea of symmetry, to show you how to get the angles using mathematics, not just eyeballing it, and also to double check on these potential angles. That's the reason I did this, okay? So let's do one more problem, and I'm going to pick this one. Now notice that this is an odd number, so you only get 3 petals, okay? And they need to be equidistant from one another, right? So if the first one sits here, you better have, like, the angle between this one and that one here is 120. It should be 120 each, right? 120, 240, 360. And this 2 is just the edge of your little petal. So 2 is not this, and it's not this. It's actually this length. This is 2, this is 2, and that is 2, as you can see, okay? Let's just again find the area, the arc length of the area of one petal, okay? Now, if I draw the tangent lines, I can see that there are 3 tangent lines. There is this one, there is this one, and there is, of course, this one, which is obvious. We know that this is going to be pi over 2. Okay? Now, you may not necessarily be able to guess what this one is, or this one, and that's why doing the math will help you. Okay? So let's start. So the area is half r squared. I squared this. Here it is, d theta. And let's figure out why did I write negative pi over 6 to pi over 6? Why am I going from negative pi over 6 to pi over 6? Okay? Some of you may be able to guess it, but if you can't, you do the math. So you add the pole when r is 0, you solve for theta. So cosine of 3 theta equals 0. That means 3 theta is at pi over 2 plus k pi, the same thing I did earlier. Then you divide by 3. And then you take different values of k. Feel free to also write k equals negative 1 and k equals negative 2. And now once you pass 2, you start repeating yourself. That's the first thing. Second thing, if you pick k to be negative 1 and negative 2, you're going to start looking at pi over 6 as something like negative 11 pi over 6 or something of that sort. Same, like 2 angles that are in the same position, but they are called by different name. So you should expect 3 angles, and here they are. And you better test them against this to see if dr d theta is not 0. So I'm just going to do one of them for you. So this is one of the potential angles. We're going to plug it in here. Sorry, yes, this is dr d theta. Now 3 times pi over 6 is pi over 2. Sine of pi over 2 is 1, and 1 times negative 6 is negative 6, which is not 0. So that works, and I guarantee you these two work as well, okay? So go back here and you put negative pi over 6 to pi over 6, okay? Please don't write 11 pi over 6 to pi over 6. I know 11 pi over 6 is the same angle as pi over 6, but you don't want to go from a big angle to a small angle. You want to go from a small to a big one. The other thing, of course, is there is a sense of symmetry here, so you could actually go from 0 to pi over 6 and multiply this by 2. So that dies, and I took the 4 out. Here it is. And I'm going to do this in detail because even though I'm using this trick again, I just want to point out something. Okay, so we know cosine squared is 1 plus cosine 2 theta divided by 2. So I'm going to solve for the cosine of 2 theta. However, I have cosine of 3 theta. See that? So the first thing I'm going to do is I'm going to change this theta into, let's say, 3u, or call it 3 theta again. It's not the same theta, but I'm just going to call it 3 theta. So cosine squared of 3 theta will have to be 1 plus cosine 6 theta over 2. Then what I want to do is replace this by that. Okay? Now that half comes out, 4 divided by 2 gives me a 2. And now this is your integrand. Notice there is no square roots, there is nothing. It's really nice to find the area of in polar curves. Now this is just theta, and that's negative sine 6 theta times 1/6. Derivative of this should give you this. Derivative of that should give you that. And you evaluate from 0 to pi over 6. And notice how 0 is so nice. When you plug in 0, you get 0 plus 1/6 sine 0. So that kills this whole piece, okay? So that leaves me with just this one. Plug in pi over 6 here, plug in pi over 6, and I got pi over 3 square units. So that should end this video. I hope it's not too long, and I hope that you found it helpful. Take care.